What we plan to do today is basically complete out the example on composite structures that I was doing last time and let Dr. Liu do that. And she'll continue with symmetric structures, basically the handout that I gave you last time. And then she has a couple of other examples also to complete, right? All right, so with that, and actually before I forget, somebody did point out to me on an example that we did maybe a couple of lectures ago, this frame example. Um, the way we computed things, the signs are a little bit important here to note. So if you remember, this was the frame with a rigid end at C and a roller at A. And the logic that we applied was that I'm going to apply some redundant AY here. Now, I said that the compatibility equation, let's see right here. So the compatibility equation I said was going to be delta A minus delta A prime, essentially saying that the vertical displacement down by at A for the real structure and minus the vertical displacement up would be 0. So hope that makes sense. Since this is down and since this is up, we are taking delta A minus delta A prime, minus, not plus. And the second fact here is that to calculate delta A for the real structure, I use the principle of virtual work. Okay. So now you know that for principle of virtual work, if I want to find displacement at A, I apply a P prime at A, right? And the actual displacement comes out to be um, uh, is positive if it comes out to be in the same direction as the P prime or the unit load applied. But note here that I'm applying the unit load upward. So delta A came out to be negative 170 as it should. Okay, but that does not mean that that this end went up. It simply means since the load was applied, the unit load was applied upwards, the delta A is actually pointing downwards. So when I use that value in the compatibility equation, maybe I'll write that as well here. I am going to use minus of minus 17066.67 divided by 392533, and the EI's cancel off. And what we get is a positive number, as we should again, because the redundant force would be pointing upwards if the displacement for the actual system is downwards. So just because I used the virtual work method and my P prime or the unit load was pointing upwards, the value I got for delta A was negative. But I should still interpret it as delta A pointing down because the unit load was upward. So I hope that clarifies your question, Nate. And if there's any other question about these things, please go ahead and post on the discussion forum. We'll try to answer it as they come along. Okay. All right, so I'll turn it over to Dr. Liu here. I think she's going to try to complete, well, maybe summarize what composite structures, what the composite structure problem that we were solving last time, and then continue from there. And maybe I'll let you use the microphone also.
Okay.
Let's see. You can just place it here. I think that should work.
Okay. It just testing, is that working?
No?
No. Or there's a no.
Oh, there's a volume here. You can try again.
Okay. Is it better now? Does it? No? Somewhat. Or can I just put it to my...
Let's see. How about this?
Testing. I need to be
Try
real
that.
close to that. Is it better? Working? Yeah.
No, I guess you might have to shout again, or you want to
Or
wear it.
yeah, I can.
Okay.
I think it's better for me to. Looks like I have to be real close to it. Okay. Okay, does it work now? Yeah. Okay. Good.
Is it? Yeah.
Okay. Okay, so last time we stopped at this example. Let me just first explain this structure a little bit first. So this is a composite structure with a beam and a truss on top of it. And we know that the member that makes this structure indeterminate is actually because of this member. Because without this member, this beam can just deform and there won't be any internal loading forces in these two members. But only when we add this member, there will be internal forces in this member. And now that this whole structure becomes indeterminate. Okay, so last time we have already solved, we have first make this structure to a determinant structure by removing this member. So those are all zero force members, A, B, and BC, and only the beam is taking the load, and the bending moment diagram is drawn like this. And then the next step is to take a cut in the member of BD and then apply a unit load within this member. And from there, okay, so here we need to notice that there's no reaction forces at A and D, and simply because that the structure itself is in equilibrium, it doesn't require any reactions at those 2 points. And from there, we can calculate those internal forces due to this redundant force loading at this point. And then now we need to solve the delta BD. So now we need to solve delta BD using the virtual work method. So there are 2 parts. First part is the virtual work method for the truss, and the second is for the beam. And as we know that there's no internal energies built up within the truss members, so this term goes away. But for the beam part, we have the virtual moment with the real moment, times the real curvature, and integrated from A to C. So let's first calculate this part. Okay. Now, to integrate, we first integrate from A to D. We have 0 to 3. The virtual moment, which is here. This is actually the virtual moment diagram, which has taken a similar form to the real one, and the values are calculated here. So now the virtual moment, we have minus 0.4 x1 times the real one, which is 4x over EI. And then plus from D to C, we have 2, 4.
All right, let's maybe try to get somebody else to tell us what that should be.
Okay.
Can you bracket it? Sure.
The m prime would be
from this figure,
minus
right?
1 point.
Actually, we have x2 going from right to left, which makes this calculation easier. So
0.4 to x6, x2, and then
yeah,
the m would be the real one, which is 30 x1.
right. Minus 30. Okay. Just click.
You just click somewhere.
Okay. And then after some calculations, we can obtain this delta BD for the determinant structure. And now the next step is to calculate the the flexibility coefficient, which is FBD-BD. So FBD-BD means that the displacement of the member BD
and we can show the diagram that will make it slightly easier.
Yeah.
So what we just found was this delta BD1, the displacement at the cut due to the actual load. Make sense? So if I were to apply a load here, those two members, what do you think? Would they overlap or would they separate? Overlap, or how many say overlap? Okay, and how many say separate? We calculated delta BD1. What did it come out to be? Was it positive or negative? It was positive. And the unit loads applied on there, would they, the way that the unit loads are applied, if the delta BD is positive, does that mean overlap or? Actually, overlap, right? So if I pull the member on top is being pulled down, the member on the bottom is being pulled up. So if delta BD comes out positive, that means overlap, right?
So the virtual load there is pulling two parts, pulling BD to each side, like this.
The virtual load is trying to make sure that whatever displacement we got due to the actual loads is negated. Since delta BD came out to be positive, the redundant load will actually come out to be negative. We'll see that in a little bit. Okay, so let's reiterate this. First of all, I think intuitively, if I were to pull down on this free end, you would see that those two members would actually indeed overlap, right? So point B up top would get compressed, and you should have an overlap, which means that to negate that overlap, I would have to push these members apart. Does that make sense? So since I'm going to be pushing those members apart, they would be in compression. The member BD would finally come out to be in compression, and hopefully we'll see that. Does that make sense?
Yeah. Yeah.
Okay. All right. So this is going to be a little bit of a dialogue between Dr. Liu, myself, and you all. Okay? All right, continue.
Okay. So now to calculate the FBD-BD, again, we're using the virtual work method. And we have to keep in mind that for to calculate this flexibility coefficient, the real and the virtual system is always the same. And that's the thing that we always that's the point that we always apply when we use this force method. So here we already have this real system here. So the virtual system will be the same as it. And so that if we apply the virtual work method, we'll have first to sum up through all the truss members gives us n prime over E. So this.
Does everyone see where this is coming from? N square L over AE. The small n, first small n is because of the virtual internal force in the three truss type members. And there would be another small n because that's also the real system. So that's why you get small n squared.
And then for the beam part, we again integral over the length. Okay. So, okay, so now let's put in those numbers. First, there are three members of the truss structure, so we add them one by one. The first one we have, so these three members AB, BD, and BC. So first, 0.1 square. And the length of this member is 3 square root of 2 over AE. And then the second one we have 0.7143 square, where the length is 5 over AE. And then the last one we have 1 square times 3 over AE.
Technically, the first two terms are minus 0.8 and minus 0.7. Those two are in compression. This guy is in tension, and this guy actually has two halves. So the length that we use here is the sum of those two halves, which is 3.
Then after that we'll have the beam part, which gives us from 0 to 3. We have the bending moment diagram drawn here for the real and virtual system. So it will give us 704 x1. And then the second segment from, again, from right to left, we have 0 to 4 and minus 0.4286 x2 over EI. Oh, actually, the bracket should be dx. And then after some calculations, we can find out that FBD, the flexibility coefficient, is equal to that. Now we need to apply the compatibility equation. So the compatibility equation is just that the delta BD for the determinant system plus the flexibility coefficient, which is due to a unit loading applied to that member, times that the real internal forces should be 0. So the unknown here we're solving for is this BD. And then now that BD is just simply delta BD over FBD and gives us minus 11.56 kips. And we see that this member BD is actually indeed in compression. And then to calculate AB and BC, we have minus 0.081 times 6. And that gives us a positive value, which is 9.34 kips. And this member is in tension. Now, after that, similarly, we calculate BC is 0.7143 minus 0.26.
Can you tell us how we got AB and BC from BD?
This,
Right. Basically from the equilibrium of that joint B, right? So if you scroll down, right? Yeah, keep going down. Yeah, so right here, this once you find that the member BD is in compression, hopefully you can see that from your intuition as well. If I'm going to pull that, if I'm going to apply a load here, then BD is going to be compressed, which is going to push back on point B, and AB and BC both would come into tension. Hopefully that makes sense. All right. So we have now forces and forces and moments everywhere in the indeterminate truss. After you do the compatibility calculation, you have pretty much everything, all the unknown internal forces as well. And I would mark with red the internal forces on those members.
okay.
I guess, yeah. All right.
Okay.
Now for the last part, where we want to find the deflection of the actual load point C. So let's maybe try to get some input from you all. How do you think we should proceed with that? Aaron, any ideas?
Virtual work.
That's right. So virtual work would be the easiest thing to do here. And to do virtual work to find displacement at C, what should I do?
Virtual work at C.
Yeah, apply P prime at C. And the response of that indeterminate system of Z would be, how would I calculate that?
Will be the same, but the value change a little.
Right, so since the actual load is also 30 kips at the same point, if I scale that by P prime divided by 30, that would be the response of the indeterminate system under the virtual load P prime, right? All of this work that we did just to solve the indeterminate system does not go to waste when we are solving the virtual system. Right? We can just reuse all of that. We don't have to do another compatibility equation, another redundant system, and so on. So that's what I think Hui is going to do. Go ahead.
Okay. Okay, as we just discussed that the virtual system will just be the same as the real one, but scaled by 1/30. Let me just write it here. And here, yeah.
Prime by 30 or 1/30.
Oh. Yeah.
That's okay. We can use 1/30.
Yes.
I think everybody understands.
Yeah, because the P prime it will cancel out with each other at the end, so it doesn't really matter. So now for the real system, we have the moment diagram is this. Note that the value at point E is minus 100.18 feet. And so that we can just use this diagram to calculate the delta C with everything scaled by 1/30. Okay. Okay. So this is actually just the beam part. So before that, we have also need to solve. We need to also add in those members from the truss structure. So here I'll just since we have calculated here, so here we have minus 756, 9.34, and 8.26. So first, let's sum up all those truss members first. We have 9. Yeah.
Go ahead, I'll go ask.
How to get the negative 100.18?
Yeah. Okay. So now that we have calculated the reactions for all the members, because before that we don't know the internal forces of the truss member because it's indeterminate. But now that we have it, so that we can just use the regular way, say that take a.
If you can scroll back up.
Okay.
So now, if BD was 0, then can you scroll back? If BD was 0, we would get minus 120 feet, right? But BD is not 0. BD is whatever 11 point something that we found, minus 11 point something. So if you scroll down now on this guy, so hang on. This guy, if I multiply this by minus 11 point whatever and add it to that number, that's where I get 100.18. Right? So we are taking the real system plus the correct value of PD times the redundant system, add them together, and we get the bending moment diagram.
And then times the length, which is 3 square root 2. And then plus the second member, 8.26 square over 30 again, then times the length, which is 5 over AE. And then the last member, 6 over 30 over AE. So those are the members of the truss structure. Now we add in the beam member first from 0 to 3.
Let's try to see if somebody wants to volunteer on what this term should be. Drew?
It's going to be the integral from 0 to 3.
Do we have expressions for this moment diagram?
Yeah. Okay, so I'll just write it here.
I see. So I think it might actually be easier to write it in terms of x1 because that would just be a linear expression rather than a 40 minus something, right?
Yeah.
But okay.
Okay, so it'd be that expression squared over 30 times the slope of the other line squared.
and divided by EI. Right.
And yeah, scale by 30. Yeah.
So in general, I think while you are completing this, go ahead.
Okay.
I'll just make a point here that I see that even on the quizzes, quite a few of you try to write a linear expression the same way that Hui wrote it here, 40 minus something linear. Right? If we just switch the axis, instead of using that x2, if I use x1, then I will not have this 40 minus something. And my integral would actually be just a single term, something x, right? Which is much easier to integrate. For example, in this case, it would simply be 100.18 divided by that length times x1, right? So uh, when you are doing those integrations on the quiz or on the homeworks, try to pick your secondary axis x1 or x2 or whatever in such a way that your calculations turn out to be easier. All right, go ahead.
So the second part can actually be more be simplified as just that.
Okay, so I think we can let everybody make sure that these integrals do indeed turn out to be what I've written out there. And the most important point, of course, of this problem is that you should be able to set up the correct underlying determinate system, the redundant system, enforce compatibility correctly, and then finding the displacement at the point of the load is not too much more additional work. Do we have anything else after this?
No.
Yeah, so if you go through the calculations, you should be able to see that the displacement for the indeterminate structure turns out to be 0.093 inches. And once again, doing those calculations of integrals is not the important point here. Setting up the integral in the first place is the most important thing, right? Any step of this big problem that was not clear? Maybe where you can take a minute and outline the important steps again.
Okay. Okay, so I guess the important steps for this problem is that first you need to realize what makes it indeterminate so that you can first convert it to a determinate system by removing this member BD.
So I think related to that, let me ask you, Matt, instead of BD, could I have cut some other member? How would you have made this or tried to find a determinate system in a different way? So we cut BD here to make it determinate. Had I cut BC, for example, would that structure be determinate? Say that again? Not sure? So yeah, let's say if BD was completely joined and I'm putting down here, but instead of BD, I cut BC. And this beam would still deform kind of like that. And those two members would still be connected to it, but they would just deform along with the B not carrying any load, correct? And since BC is cut already, that is also not going to be carrying any load. So we could cut any of those three members to make it determinate. But BD is the easier choice here because it makes rest of the calculations much more easy. Okay, so this structure has a degree of indeterminacy 1, which means I need to remove one redundant unknown. It could be any of those three plus members. Okay, so and the other thing here is that we are actually cutting the member. We are not really removing it. Because we are cutting the member, we need to account for what is the displacement at the point of the cut. And to do that, we are using the virtual work method by applying equal and opposite unit loads at the point of the cut. I hope that point So this is the most important point for composite structures. For other types of composite structures, you need not cut any of the truss members. You can possibly remove a support from the beam. So that would be basically up to you to decide what would be a good choice to make, what redundant element or force you want to remove. Okay. All right. So after this point, I think once you have this concept clear, using compatibility and all that, I think you've already done that in your homework problems as well. So maybe if there's no further questions, I'll let we proceed with the last topic. Go ahead, Nikhil.
So if there is no 30 kip force at C, and you define the deflection at C, if you put a P prime there, if you add a P prime there when you're doing the virtual work, do you have to do the whole force method again for the system?
So I think what you might be thinking of is that if there is no real load here, maybe the real load is somewhere else on the beam here or somewhere else, and you want to find the displacement here. So if you do not have, if you're not being asked to find the displacement at the point of the load, then you do indeed have to do the real, do the entire machinery again for the virtual part. You have to solve a real system, you have to solve a virtual system. If the real and the virtual system are not the same, you have to do all of that. And I believe on your homework 5 last problem, it is kind of like that. You have to do that again, right? So yeah, so even in this problem, I could ask you potentially, you know, I'm applying a load at C. What is the horizontal displacement of B? I could potentially ask you that. In that case, you would have to apply a horizontal P prime at B, resolve the entire system, right? So yes, these problems can very quickly become, any indeterminate system problem can become very quickly, it can become very cumbersome, which is why we are going to use computational or computer methods as I'll start next week. But I think the last thing here was deflected shape, right? So maybe you can draw deflected shape or I don't know if you have.
Yeah.
You have it? Okay.
Yeah.
So yeah, go ahead.
So the deflection shape for the beam is just actually it's in this shape, right? And then for the truss members, we know these two are in tension and BD is in compression, so it will move with the beam while compress in BD a little and stretching in AB and BC.
So for most indeterminate or composite structures, the deflected shapes are fairly complicated. But yeah, you really have to think through it and try to come up with that. Question, Fonzie?
I think the maximum moment of 100.18 is not correct. Supposedly it is like 113 something. Because if you use the moment equation for d minus 9.34 something, you substitute the x with 3.
So that part could be incorrect, but let's check. Can you go back up quick? So the first number we have is minus 120 kip feet, and the second number we have is minus. So you have a calculator, right, Fonzie? Can you do minus 120, and what is the value of BD that we got?
11 point minus.
So minus 11. So it would become plus 11 point whatever that was times 1.714. And what does that come out to? 1.18, right? So maybe there's a error in the expression that you coded up the way.
Here.
Right.
Okay, so maybe I'll just change that.
We just write that in terms of x1.
Yeah, that's what I was suggesting. So let's remove that and call that. You can delete it.
Just that.
That
okay.
way. And let's just write it as minus 100.18. Minus 1.18. And that length is how much? Square root 3 over 2. 3 square root 2, right?
Yeah.
C square root 2 times x1. Does that make sense? Oh yeah. So I'm not sure what. Yeah, this length is actually 3 feet. Is that right? I don't have that problem with me right here.
Yeah.
Yep, 3 feet. So load 3 root 2.
Okay.
Right. So that would make it the integral also easier. Okay. All right. So let's go to the symmetric topic. We don't have too much time, but hopefully we can finish it.
Okay. Okay, so now let's look at the symmetric structures. And first that we need to know that why we want to use symmetry or anti-symmetry of the problem is because that for some highly indeterminate structures like those the frame structure at the beginning of the nodes, we usually need to make a cut at each column so that which makes the problem simpler. And that is actually to utilize the advantage of the symmetry of the structure. So here, so for example, in this truss structure,
Let's ask somebody, Daniel, you want to tell us in this truss structure, what's the degree of indeterminacy of this truss structure?
4.
And how do you come up with that?
Because if you cut
Okay,
down
so
the middle, there's 4 members that are.
There's 4 members. So I guess on the left we have a pin, and the right we have a roller, and there are 3 bays, so to speak, and all the 3 bays have that cross, right? So if I remove one of the elements of one of the diagonal elements from all the 3 bays, would that be determinate? Right? If I remove one of the diagonal members, I have 2 diagonals. If I remove one of the diagonal members, everything becomes a composition of triangles. Composition of triangles is determinate in trusses. So since I'm removing 3 members, degree of indeterminacy is 3. Okay. And yes, like Hui mentioned, the point of using symmetry is to reduce the number of redundant unknowns. You could have, if you were to solve the symmetric half of the problem, you will usually have half the number of unknowns to solve for. If your degree of indeterminacy for the big symmetric structure is 2, you solve half of it, your degree of indeterminacy would be 1. So it would be much easier to solve. Okay.
Okay, so now let's look at these few examples of indeterminate structures, beams, and frames. So first, let's see how would these structures respond to those forces. For example, this one subjected to a uniformly distributed load with a pin here and a roller at 3 locations. So what do you think will be the deflected shape of the structure? Anybody?
So maybe we can do this as a in-class exercise. There are 3 examples. Draw the deflected shape, 4 actually, right?
But the fourth one.
Oh, the 4th one I've already drawn, but
Yeah.
maybe for all of those examples, draw the deflected shape, mark what is the symmetric structure you would solve. Okay. Okay. So let me see if I can try to complete that. I'll do one of them, and then I'll let you guys do the other 3. So for this structure, if I clearly this is a symmetric structure, right? I have an axis of symmetry, loading, and the structure and the boundary conditions, everything is symmetric. So if I were to draw the deflected shape here, it would be something like that, right? If this is the deflected shape, then clearly I can see that I can draw half of the structure. If I pick this half of the structure and solve that half, then it'll be a lesser number of unknowns to solve for, which I can do by solving this problem. So I have this member. I do have a roller here, and what should I have at this point? Say that again. Moment and shear. So how can I get some displacement here but no rotation, correct? That's what I need. What kind of boundary condition would that be? So it would be like a moment with a roller support, that condition. And I would still have the applied loads. If I were to solve this problem and replicate it on the other half, then I would have solved the original problem. The original problem, as you can see, if I remove the center two supports, degree of indeterminacy is 2. Here, what is the degree of indeterminacy? Degree of indeterminacy is 1, because if I remove this support, it's now just a simply supported beam with an overhang, which is determinate. So if I put that back in, that's adding only one unknown, the moment at that point. There is no vertical reaction at that point, right? So clearly this is an easier system to solve than this. So that's the, well, we had 219, so I'll just go ahead and do this and we'll continue with the example next time. For this guy, is this symmetric? No, it's anti-symmetric, right? So as long as the structure is symmetric, boundary conditions are symmetric, but the load is anti-symmetric, you can still make use of this idea of symmetry and anti-symmetry. So here, if you were to draw the deflected shape, you would get something like that. And what would be the symmetric half here? It would be something like this guy. Let's put a pin here and a roller here and a roller here with a load P applied at that point. Solving this half of the system and replicating it or reflecting it on the other side would give me the original problem. Now this part is a little more interesting. So maybe what we'll do is we'll stop here. Next time when we come back on Monday, the first thing we'll do is one of these problems as an in-class exercise, and then we'll switch into programming or using computer methods to solve these complicated problems to make our lives simpler. Okay, so let's stop here, and I'll see you back on Monday.